Hello everyone, welcome back to my channel. I am Vamshik Shetty, pursuing second year BE in Sri Venkateshwara College of Engineering, Bangalore. Today we are going to discuss about the a fascinating topic that is revolutionary the field of data compression, that is Huffman trees. You might be wondering what are Huffman trees. Well, they are a type of binary trees used for data compression, but why should you care about them? Because understanding Huffman trees can help you save space and make your programs run faster. So let's dive in and explore this amazing concept together. Today in this video we are going to discuss about the introduction of the Huffman trees and the Huffman algorithms, encoding and the decoding process, where in the introduction to the Huffman trees and the encoding types of the Huffman trees is discussed. In the Huffman algorithm, a brief explanation about the Huffman algorithm is given in this presentation. In the encoding and decoding, we have taken an example for the Huffman algorithm to know about the Huffman trees in a better way. So let's start the introduction of the Huffman trees, where the Huffman encoding is one of the most important file compression methods. In addition to its simplicity and versatility, it yields an optimal, that is minimum length coding. This technique is known as Huffman coding, which was developed by David A. Huffman in 1952. The process of building Huffman tree involves analyzing the frequency of each character in the input data and creating a binary tree where each leaf node represents a character and its frequency. Suppose we have to encode a text that comprises symbol from n symbol alphabet by assigning to each of the text symbols some sequence of bits called the code word. There are two ways of encoding, that is fixed length encoding and the variable length encoding. Now let us discuss about the a brief, that is brief types of the encoding. The fixed length encoding. This method assigns to each symbol of a bit string of the same length, that is m into m power greater than log 2 power n. This is exactly what the standard ASCII code does. One way of getting a coding scheme that yields a shorter bit range on the average is based on the old idea of assigning shorter code words to more frequent symbols and longer code words to less frequent symbols. Whereas in the variable encoding, this method assigns code words of different lengths to different symbols, introduce a problem that fixed length encoding does not have. To avoid this complication, we can limit ourselves to the so-called prefix-free or codes. In a prefix code, no code word is a prefix of a code word of another symbol. Hence, with such an encoding, we can simply scan a bit string until we get the first group of bits, that is code word for some symbol, replace these bits by this symbol, and repeat this operation until the bit string is reached. Let us move on to the Huffman's algorithm, where in the step 1 we are going to initialize the n one-node trees and label them with the symbols of the alphabet given. Record the frequency of each symbol in its tree's root to indicate the tree's weight. More generally, the weight of a tree will be equal to the sum of the frequency in tree leaves. In the step 2, we are going to repeat the following operation until a single tree is obtained. Find two trees with the smallest weight, make them the left and the right subtree of a new tree, and record the sum of their weights in the root of the new tree as its weight. A tree constructed by the above algorithm is called the Huffman tree. It is defines the man describes the above the Huffman code. Now we are going to discuss about the encoding with the Huffman tree. We can discuss with the example also. Now to encode a message using Huffman tree, we first need to create frequency table of all characters in the message. The characters with the higher frequencies will be assigned shorter bit codes, while the characters with the lower frequencies will be assigned longer bit codes. This is because the shorter bit codes take up the less space and can thus help us to compress the data. In the given diagram, we can see the symbol and frequency are listed in the table, where the shorter frequencies are listed in the left side and the more number more longer frequencies are listed in the right side. In this way, the encoding is done, where once we have the frequency table constructed, we can use it to build an Huffman tree. We start by creating leaf nodes for each character based on their frequencies. We then combine the two new nodes with the lowest frequencies into a node which becomes the parent of the two nodes, and we repeat this process until we have a single root node that is given in this figure, where the 0.15 and the zero point 0.1 has been combined to get a new node that is 0.25, and the 0.25 and the 0.35 has combined together and got a new node that is 0.6, and the 0.2 and the 0.2 of the C and D has combined to get a 0.4 of the another root node, and at last the 0.4 and the 0.6 has been combined to get the a single tree root, where the bit codes for each characters are determined by traversing the tree from the root to the leaf node, assigning as a 0 for each the left branch and 1 for the each right branch. That is, in the left side of the leaf node we have given as the value of 0, and in the right branch of the tree we given as the value of 1 to get the ASCII value of the code. Now let us discuss about the decoding with the Huffman tree. To decode a message using Huffman tree, we start at the root of the tree and follow the path that corresponds to each bit in the encoding message. As we move down the tree, we keep track of the other characters we encounter until we reach a leaf node. The character at the leaf node is the decoded symbol. We then repeat this process for each bit in the encoded message until we have decoded the entire message. The example of the ABCD again taken here, and the frequencies as given by the in the question only, and the code word was listed, where the A code word is 11, and the B code word is 100, and C is 00, and D is 01, and the underscore code word is 101. Hence the DAD is encoded as 0 1 1 1 0 1, and the 1 0 0 1 1 0 1 0 and 01 is decoded as BAD underscore AD from the given code word table. In the compression ratio, we are going to find the compression ratio after the code word is listed. With the occurrence of the frequencies given and the code word length obtained, the average number of bits per second symbol in this code is, where we have multiplied the two number of code word with the 0.3 of 35 of A, and we have added with the 3 code word into the 0.1 of B, and added with the 2 code word with the 0.2 frequency of the C, and added with the 2 code word with the 0.2 frequency of the D, and 3 code word with the 0.15 of the underscore. And by solving this sum, we are going to get about 2.25. Had we used a fixed length of encoding for the least same alphabet, we would have to use it at least 3 bits per each symbol. Thus, for each symbol example, Huffman's code achieves the compression ratio. Now we have came across the last part of this video, that is conclusion part. In the conclusion, we have learned that Huffman tree is a powerful tool for data compression and encoding. Through its efficient algorithm, it can reduce the size of the data without losing any information. We have seen how to build a Huffman tree, encode and decoding the message using it, and compared it with some other comparison algorithms. Understanding the Huffman tree is very important not only for computer science students but also for anyone who deals with the large amounts of the data. It can be used for various real world applications such as image encoding and data compression. By mastering this concept, you can improve the efficiency of your work and save valuable time and resources. Yeah, that's it for this video. Thank you for watching. For more videos, please like, share and subscribe the channel. Thank you.